All right. Good afternoon, everybody. Happy Thursday. So, just a sort of, yes, recap or just sort of a few updates, I guess. So basically, I'm gonna have probably a homework assignment posted up sometime next week. So we have so far five assignments. I'm trying to have around maybe seven or eight in total. So I guess two or three more, in this month is kind of my goal for right now. So we're gonna focus mostly on graph theory type stuff for most of this month. So probably have an assignment on just sort of the basic traversals, so the content from last time's lecture, maybe a few extra questions on top of that. That's some greedy approaches, some greedy algorithms involving graphs, and then dynamic programming involving graphs. So something along those lines. So probably around two or three more assignments left. Just to sort of, I guess the exam will cover stuff after the midterms. So graph theory, the B trees. Let's see what was actually covered after exam one. So yeah, B trees, graph theory. So whatever we covered after exam one is mostly gonna be on. So it will be just sort of the content after the midterms. So I guess a big chunk will be graph theory, of course. I think it was two, three trees also was covered as well. Can't remember what else we covered, but those were like the main ones, I think. So yeah, something along those lines. Um, so anyway, so next Tuesday, we're not going to have a live class because I'm going to have the faculty senate meeting. So another one of these. So it's that time of the month for that. So I'm going to have a video over the weekend I'll work on and I'll post it up onto my YouTube channels. I know it's kind of back and forth between YouTube and WebEx recordings, but that's how it is, I suppose. So I'll sort of send the link in the Canvas announcement. So you'll have the video. So on Tuesday, there'll be no class, but that pre-recorded video will be our substitute for that Tuesday class. Then next Thursday is going to be Veterans Day. So there'll be no class on next Thursday. So next week, there'll be no live class. So one pre-recorded lecture and then one just sort of no class at all because Veterans Day. So that's going to be our next week's schedule. So let's go ahead and go back to the board and I'll do a screen share. Let's go ahead and just sort of resume from last time. So let's start screen one. So I guess last time I sort of went over a few applications. I went over depth first search and did a couple applications of depth first search graphs. So this one was actually for finding all the strongly connected components in a graph. Also topological sort last time as well. So a couple of examples on depth first search. So I guess our next homework, which I'm going to try to get it working on this weekend, but anyway, it'll be around these topics. So probably just use that first search for topological sort, for the strongly connected components of a graph. And I also could ask you a couple of conceptual questions on depth first search. That's going to be the assignments. So I'll work on it over the weekend and sort of also even go over it in the video probably for next week. So we'll have that. So the next sort of topic I'm going to cover is going to be, I guess, breadth first search is the next one. So you might have learned this in 302 as well, but I want to just go over it just so, we can kind of build off of this. Might have been a while since you've done this, so I guess I'll just go ahead and just go over it here, today's class. Okay. So basically for breadth first search, well, unlike depth first search, it's not going to be recursive. So it's, I guess, not recursive is the most important sort of bullet involving breadth first search because, of course, recursion is never fun. It's always, of course, magic in terms of how it works. So a breadth first search algorithm actually is going to, so basically it's a single source shortest path algorithm on an unweighted graph. So unweighted graph really means that it's a graph that has no weight. So every edge is no number, so all the edges have the same weight, basically. And single source shortest path algorithm really means that we want to find a shortest path from one selected node to every node in my graph. So basically, if I choose some start node, breadth first search will find the shortest path from that start node to every node in my graph. Whereas depth first search does not guarantee this. So let's go back for a second to my depth first search nodes so we can just sort of talk about this again and see where is it. Let's see, somewhere here. Oh, it's here somewhere. I don't know why. Oh, graph theory is whatever it was. Okay. So, um, let's say, for example, above over here. So we had these pi values, which was sort of our predecessor nodes, which is a way to kind of construct our actual paths produced by depth first search. So this tree right here, or this forest, gives you the actual order in which we traverse nodes in our graph. So, for example, from A to E, the best possible path is just this edge right here from A to E. But that first search, it found the path from A to E, but it actually went from A to B, A to B, B to C, C to F, and F to E. So it found this path, essentially. So I'll just mark it for a second. It found, on the right, okay, there we go. So it used this path to get from A to E, which is definitely not the best path. So since it's unweighted graph, then the path with the smallest number of edges is the best path. So that first search didn't find it. Now, maybe it could have gotten lucky and it could have found that the best path from A to E was this edge, but it happened to choose this path. So that first search does not guarantee the best possible path. Whereas breadth first search, actually, the way it's going to work is going to guarantee the best path from our start node to every node in the graph. Just to first mention that. So it's going to actually traverse the graph in level order. So depth first search traverses it in depth order. So it always keeps going one level every time. Whereas breadth first search is going to first expand for a node all of its sort of direct one edge neighbors, expand all the nodes in that first level, and then go to the next level and so forth. So it's going to use, so it uses a first in, first out queue to maintain the order of nodes processed. Whereas depth first search uses a stack because it always has everything, we push elements onto a system stack because it's recursive. So the stack actually maintains the order in which we traverse through the nodes in the graph. Whereas breadth first search uses a queue to maintain that. So that's basically the main sort of points here on breadth first search. So I'm going to now go over the actual, I guess, pseudocode on breadth first search. And then I'm going to use an example just to show how it works. And this will not take too much. I'm not going to really go, I'm not going to do, so for depth first search, I covered other sorts of applications of it. Here, I'm not going to, I'm just going to just do breadth first search once and then just kind of leave it like that. But anyways, go ahead and just go over the pseudocode for this. So it's going to be actually BFS is the name of the function. Now, once again, have G and have S. So it's actually, I don't know why it's called breadth first search. It's really breadth first traverse. So we're traversing a graph a certain way. But of course, it's called breadth first search, although you could search the graph, but it's really just a traversal type. It's really what this is. And then G is going to be your graph, which your graph is really a set of vertices and edges. And S is going to be your start node, or your source node, sorry. So this graph, this algorithm is going to try to find the shortest path from S to every node in my graph. let's go ahead and write the pseudo code for this. So the first step we're going to do is for each vertex. So let's write the code here. So for each vertex, U in sort of it's kind of a weird notation used here in the book. Basically, for every single vertex that's not S, so let's go ahead and cycle through every vertex in our graph that's not S. And we're going to color each one to be white, so we're marking them as all unvisited. So from the book again, and then the distance, I guess infinity, and then u dot pi is going to be empty. We're simply just sort of initializing all of the vertices of our graph in this portion. And S is going to be your start node. So then S dot color is going to be gray. And then I'm not sure if it's the right way of spelling green. This is G-R-A-Y and G-R-E-Y. There's one is the British way, one is the American way, but gray. We use the word gray. And then we're going to say S dot D's in discovery time will be 0. S dot pi, well, it's going to be, of course, going to be empty because S is your starting node, so S has no predecessor. And then what's going to happen is we're going to have our queue. Our first in, first out queue will be initially empty. And then we're going to now in queue. We're going to in queue. So we're going to basically insert S into our first in, first out queue. So letter Q right there is going to be just our first in, first out queue. And Q, just remember, it will push to the back of the queue. And then while the queue is not empty. Obviously, initially it won't be because we just inserted S into our queue. We're going to have U is going to be just DQ. So we're going to remove the element from the structure. So remember, for DQ, we remove from the first in the line. So remember, NQ inserts to the back of the line, and DQ removes from the front of the line. So we're going to remove an element from the front of the line. And then for each V in U's neighbors list, do the following work. We're going to check and see, well, if v dot color is equal to white, so it means that we haven't processed this node just yet. We're going to set the color to be gray, which means that it's not processed, but we're going to put it into our queue. And of course, we're going to set its discovery time to just basically be u d plus 1. I think I can set discovery time here. Cool. And then v dot pi equals u. So we're going to set v's predecessor is going to be u. And then we're going to basically enqueue v into this queue. And then we're going to have, we're going to indent back. So this is going to be not part of the if block. We're going to set u's color black, which means that this node has been fully processed. Let me zoom out so we can see all of this. Go ahead and try to do the following. I'm going to put some lines here to kind of denote it's going to be the entire function sort of scope. And we have this loop right there. We're going to have this right here. Let's see. here. And we're gonna have that's kind of how we can see the blocks, I guess, for this pseudocode. So anyway, mistake. Good. No, it's actually fine. That U is actually not part of the if. Yeah, because it's going to basically it's not part of the for either. So probably should be moved over a little bit more to the left. My mistake. After we push all of U's neighbors V onto our queue, we're officially done with this node U. So there we go. So there's going to be our pseudocode. So what's going to happen is all we're doing is we're going to push all the neighbors onto the queue at one time. So the next element to be processed off is going to be the next element in that same level. And then when the next level occurs, so I guess it's kind of hard to explain this, but anyway, this is going to basically traverse in that level order. So let's go ahead and do an example of this so we can actually make sense of it. But of course, I'll put one more note over here is that I'm going to sort of zoom in on this so we can write this a little better consistently. Um, so basically, for a node U, U dot D denotes the level index, or what level this node is in. So discovery time, but it's going to tell us what level, how far away it is from our start node. So we'll see that in a second. So let's go ahead and draw an example graph and just trace out breadth first search on that, and then we can sort of move on to other things. So it shouldn't take too much long, maybe 10 minutes or so more, I think, but let's see how this goes. So let's look at an example. Let's see. I'm going to choose, I guess, maybe I'll choose S as my starting node, sub S, and I'll have these A, B, C, D, E, F. Yeah, I'll go with that. I'll add some edges here. It doesn't really make that straight. Let's try one more time. Oh well. So anyways, let's go ahead and add the edges here into this graph. This will be a directed graph example. I'll just go ahead and I'll put this here. Is it good enough? So some arrows here like this, that. I'll go ahead and put this here as well. Let's see. Okay, so I guess this is a good enough example graph. So basically here we're going to have S will be our starting node. So we're going to mark this as our start. So I'll put a line here just to note that is my starting node. And for breadth first search, we're going to basically pick a start node. So I'm going to pick S just for right now. So we're going to go through every single node in this graph. I'm going to mark them all as sort of as unvisited. And I'm going to, I guess I'll use, I'll put a number above. But right now, though, these numbers are going to be just basically, I guess it has as an infinity. So I'll put as infinity, I guess, for right now. We're going to update these as we go. So I guess the blue numbers there are going to be the discovery times, and the red is going to be that pi value, or basically that predecessor. So I'll put in here, I'll just put pi. I'll do like this just to sort of make it sort of clear, distinguish these, I guess. So we're going to store each node's predecessor, so we always can construct the paths, basically. And for S, will be also like that. And discovery time for S is going to be just 0. We're going to mark it as gray. We're going to pick S as our starting node, of course. So now what's going to happen, I'm going to put the Q right below over here. So we just sort of zoom out a little bit so we can see all this. And I'm going to put the Q here. So I'm going to just copy this. Paste it below. Good enough. This is going to be our Q. Let's call it Q, I guess. That's going to be our Q. So the first thing we're going to do is we're going to push S onto our Q. So S is first on our Q, just like that. And we're going to run this algorithm. So obviously our Q is not empty because we do have S currently on our Q. So we're going to go ahead and we're going to pop S from the Q. Or actually call it DQ operation, but in our while loop, we're going to first pop S from our Q. And if you look at our sort of our pseudocode, we have this for loop, which is going to go through every neighbor of S. So right now for S, we have two neighbors, A and C, and they're both not marked as gray. So what's going to happen now is we're going to go ahead and insert them both into our queue. So the first thing we're going to do is we're going to color them both to be gray. I guess blue will be gray, I guess, in this. So we're going to mark them as both gray. And then what we're going to do is we're going to set their times to be basically just, so UD plus 1, basically. So UD in this case, well, it's going to be S dot D. We're going to add 1, so we're going to basically set these to both be 1. So according to our code, we just first take whatever was in U dot D. In this case, S is going to be our node we just popped off of the Q. And then its distance is going to be 0, so plus 1 is 1. So we assign A dot D and C dot D to S dot D plus 1, just like that. And then we're going to set their predecessors. In this case, they're both going to be just S. In this case over here, we can see that, well, we just sort of store that A's predecessor is going to be S, and C's predecessor is also going to be S. That's how we use these predecessor values to sort of construct our tree, or our paths, or our breadth first search tree. So now what's going to happen is, well, we're going to mark this node as red. It's been processed. Then we're going to go ahead and push A and C onto my queue. Okay, so now we have those, and then we have to run that loop, and we keep running the loop as long as our queue is not empty. In this case, it's not empty, so you have to keep working on this. So the next thing we're going to do is going to pop A from this, these different color pens, so that way you can sort of see what was there before. Too much. Let's put a single slash like that. Maybe that'll be a little better, so you can at least see what was there before when you're looking at the notes. So we're going to pop A from our queue, and we're going to go through and just go through every single element, every neighbor of A that's not sort of, that's marked as white. So right now, well, let's go ahead and first look at B. So B actually is marked white, so B has not been visited. So we're going to go ahead and set B's distance, or its D time, to be really just A dot D plus 1. It's going to have the value of 2. All we do is we just sort of set the neighbor node's discovery time the predecessor is +1. So going back to the code, we had that line that had b dot d equals u dot d plus 1. Well, in this case, u dot d is a dot d plus 1. So we add 2 to that, just like that. And the predecessor is going to be a. That's where so we came from a to get to b. And we're going to go ahead and push b onto our queue. And then we're going to mark this node as gray. Then we have other elements as well. So from A, we also have another neighbor, which is going to be E in this case. So E has not been marked gray. So we're going to go ahead and sort of take E, mark it as gray, and its time is going to be set to 2 because we just take the predecessor node A dot D plus 1 to set E dot D. And then we're going to set its predecessor A because we came from A to get to E. We're going to push E onto our queue. The last neighbor of A is going to be D, and we see that D is marked as white, which means it's not been visited yet. So we're going to mark it as gray, and its distance, or its time, will be set to 2 because we're going to go from A's distance, which is going to be in this case for our pseudocode, A will be U in this case, so U dot D plus 1 equals B dot D. So we take that 1 added to D's discovery time like that. Going to mark, we're going to set D's predecessor to also be A, and we're going to insert D onto our queue. So we can see here, and I'm going to go ahead and mark this as processed. So we see here that what happens is that in our queue, we always maintain the level order because we see here we had S initially. S's one sort of edge neighbors are A and C. And these two will get processed before B, E, and D are processed. So B, E, and D are the one sort of hop neighbors of A. But we're going to first process A and C first, then we're going to process B, E, and D next. And then let's say after the next element that gets pushed onto this queue will be elements that would be on the next level. But that will get processed after we process everything on the second level. So we see how the queue actually maintains this sort of level order. So now what's going to happen is we're going to pop C off of our queue. Looking at C, well, C has actually no neighbors. So we're done. Nothing is pushed onto the queue. So we'll mark this as processed, and that's it. Now we're going to process B next. Go ahead and pop B and process it. So B has one outgoing neighbor, which goes to E. But we already put E onto our queue. We marked it as gray from A, so we're not going to actually do anything. So B has nothing else to really be done. There's no work for B. So mark it as processed. Now let's look at E next. So we're going to go ahead and pop E from our queue. And E has really only one neighbor I can see here. It only goes to G. And G has not been marked yet. So we're going to go ahead and now set G's color to be gray. Its distance is going to be really E's distance plus 1. Make that 3. And the predecessor of it is going to be E, because that's the predecessor of G. Then we're going to push G onto our queue. So now what's the next element to be processed? Well, we got to process D next. So we're going to go ahead and pop D from our queue. And for D, well, it does go to E, and it does, wait a minute. Oh yeah, I already processed C earlier. Okay, I guess I kind of got brain fog right there. So it has a neighbor C, but we already processed it through A earlier. So we don't want to push C onto our queue. And D also goes to E as well, but we actually, oops, I should have marked this red earlier. E has already been processed. My mistake there. But yeah, we already processed E earlier. It's not marked as white. It's marked as, it should have been black, but I used gray back since it's red, so it means it's been processed. So D has nothing else to do at this point. So now we can go ahead and mark as D has been officially processed. Now we have to look at our next element on our queue, which will contain G. We pop G from our queue, and G only has one neighbor, which goes to F, and F is marked as white, which means that's not been visited yet. So we're going to go ahead and now mark it as gray. Set its time to be G's distance plus 1. The predecessor is going to be G. Then we're going to push F onto the queue. And of course, then we're going to then mark G as processed. And then what's going to happen is, well, our queue is not empty yet, so we have to go ahead and pop an element off. We're going to pop F from this heap. And we see here F has only one neighbor, B, but B is not marked as white. B is, in this case, red. So that means it's been processed. So we're not going to be able to do anything there. So we're going to just basically mark it as processed and not push anything onto our queue. Then we see our queue is now going to be empty, and we're done. So we have these nodes processed where you notice here that these numbers really denote sort of a level index. So if you look at this, we did process nodes level order. So you first processed, let's say the green marker here. So you first processed S, of course. Then we have A and C. Then we processed all of these. Then we processed just G. Then we processed, I guess, F. So I'll redraw this in a second, but we kind of processed it in level order like that. And by doing that, because breadth first search processes nodes in that order, it's going to give us the best possible path. Because we have, for example, S going to C. Well, the best path from S to C is going to really be one edge from S to C. So it's going to process C. So it's going to process this edge first before this edge from D to C is going to get processed. Because we always do it level order, so we're going to first push all of S's neighbors, A and C, onto our queue first before D is put into our queue, which means that we're going to process C before D could be able to process C. That makes any sense. So because of that, the best path from S to any node, the first instance we discover it, when we pop it off of the queue, that's the best possible time. There's nothing better than that because it was a better path. It would have been actually processed earlier, is the idea. Because we push onto the queue as soon as we see a neighbor of S. So that way, C is processed by S before it would have been processed by D. So that's why it's going to guarantee it. So there's no way that this is going to be able to process C through D, actually. It's impossible because S discovered C first. So it's going to process all of its neighbors one by one like that. So it's going to cause this to be a very, it's going to be a very nice short path. And we can see here, these blue numbers, discovery numbers, are actually the account of number of edges needed. So from S to F, it takes 4 edges to get there. So that those numbers tell you the actual path length, which in this case is going to be number of edges in that path. Then from S to C, it only has 1 edge. From S to B, there's going to be 2 edges. So then the number will tell you the actual path length. Let's go ahead and draw the breadth first search tree for this graph, just so we can kind of look at this. So I'm going to have S. S has A and C. So we can actually use the predecessors to compute these. So I'm going to have just A and C over here. Then from A, we have B, E, and D. And then, let's see, from B, we have B. C has nowhere else. Okay, so he has G. Circle these in. I'll zoom out so you can see all this in a second. It's going to be our breadth first search tree. So for breadth first search, the tree is going to be a little different than a depth first search tree. I guess I'm trying to zoom a little bit. I think we can kind of see that. So this kind of tells us the path from S to A to B and so forth. So these arrows in that breadth first search tree, we just reconstructed that using a predecessor values. So knowing that F's predecessor is G, G's predecessor is E, E is going to be A, and A goes to S, we can actually construct these paths using these predecessor values. So in fact, if you were to actually write a program to output the actual paths, I want to find a best path from S to G. You're starting from G, the predecessor is E, so you have G, and you push E onto your stack, push A onto your stack, and push S onto your stack, and the stack from top to bottom will give you your actual path from S to G. But that's more of a 302-ish thing, but that's how you would do this. So for a breadth first search, since it's going to sort of trace or traverse this graph in level order, this tree will be kind of a bit more, how shall we say, more fuller kind of tree, if you will. Whereas depth first search is sort of very narrow looking tree. So looking back, let's go back to our notes for a second here. For depth first search, it was a very narrow, very skinny tree like this. And typically that's going to be the case because usually, unless it's a very full, very big, very dense sort of graph, it's gonna be a very skinny tree like that because you always go one path, you back up, so it's not gonna be so sort of full like that. So for example, over here in this graph, it would actually have A would go to B, A would go to E, so these two would be kind of children of A in this tree. And B has several neighbors as well, so it'd be more of a fuller kind of tree. This is a very skinny tree. So typically, depth first search would have a more skinnier tree like that. And breadth first search is more of a fuller tree. But I guess the nature of how we traverse is the reason why breadth first search does produce the best possible path. Looking at this, I guess I won't go back, but looking at depth first search, it could find a longer path potentially. I mean, there's a chance we could have, from S to C, it could have found a longer path potentially. Depth first. Depth first search, however, will always find the best possible path. So anyway, that's how we do that. So we're going to also go over later in this semester, or later in this month, I would say, Dijkstra's algorithm, which is going to be just a weighted graph version, really, of this, a breadth first search. So we're going to kind of revisit this idea later on. Let's first go over the runtime analysis for this, and we'll go into contents. So pretty simple runtime analysis. Basically, every edge is looked at, really, just like for depth first search. So we traverse this graph, every edge is going to be investigated. So basically, even if let's say, for example, when I went from D going to C, I picked this edge earlier. Well, this edge is not going to be, I mean, we're not going to push C onto our queue from D because we already pushed it from C. But we have to look at this edge in order to know that this node has already been processed. So really, every edge is looked at once. So the runtime for this is going to be really simple, just O of E plus V, or you could just say O of E, really. They use this E plus V sometimes because, well, if it's a sparse graph, it's O of V, dense graph, O of E, but really it just, the edge count is going to give you the runtime, really. And of course, it gives you the best runtime or shortest possible path, and the idea is that because, so when we actually discover a node, when we actually discover it, that's the best possible path. There can't be a better one. Otherwise, if it was, it would have been discovered earlier. So you actually can make a proof for this using a proof by contradiction that breadth first search will find the best possible path. So maybe it could be an exercise for homework, just using a contradictive proof, prove that breadth first search does find the best possible path from your source node to every node in your graph. It only works for a single source node. So breadth first search is not going to find the best path between every pair of nodes. So because we chose S as our start node, then it's going to find the best path from S to every node in my graph. If I want to have the best path from A everything in my graph, then I would have to run breadth first search and choose A as my start node. So I would push A onto my queue initially, and then from there, do the same work, but an example right here, I first push S onto my queue. I set S's distance to 0 and push S. I can run breadth first search on node A. And I would go ahead and if I run breadth first search then, it would give me this tree where A would be the root of this tree, and it would give me the best path from A to every node in my graph. So it's not going to work for every single, so if I run it for like one node, it won't work for every single pair, only for that one single source to every node. Now, if I want to have the best path between every pair of nodes in my graph, I have to run breadth first search on each node as a start node. So I run breadth first search on S, breadth first search on starting node A, breadth first search starting node B, and so forth. Then I would be able to construct sort of the best path between every possible pair of nodes in my graph. But since I only chose S right there, then it's going to only pick, it's going to find the best path from S for all my nodes. It won't find the best path from A to B, only from S to A, S to B, S to D, and so forth. So I think I've rambled enough on that. So anyway, that's basically sort of breadth first search. So let's go ahead now, talk about the next sort of topic. Right, greedy algorithms is the next topic. We're definitely at that point finally. Let's go ahead and start a new board and go over greedy algorithms. There's not much to say about this, but I'll just talk a bit about greedy algorithms here. So it's really just a paradigm, or it's a paradigm or a class of algorithms. So far this semester, we've covered divide and conquer algorithms. So that was also a set. Let me put this a little bit, slash. It's a set of algorithms. Remember, we had divide and conquer. We used quicksort, a selection problem, median. That was selection. The medians. That was selection. Of course, we had the Strauss-Zen's algorithm for multiplying two matrices. We also had the multiplying two numbers together. Those are all divide and conquer problems. They all had that same, they share that same thing in common, is that they all kind of broke the problem into smaller pieces and attacked each individual piece separately. That was the idea. So that was a class of problems. So greedy is also a class of problems. And the way it works is that, so an algorithm, so a greedy algorithm, sort of chooses the next best immediate step. Now, this is actually not always the best idea for every single situation, but for this class at least, we're studying sort of offline algorithms where the input is kind of known in advance. So really, a greedy approach is not a bad idea. If you're doing online algorithms where it means that the input is not known at one time, then a greedy approach can actually be worse. But for this class, of course, greedy approach isn't a bad idea. So it picks the next best step. Doesn't really look into the future. Well, sometimes being greedy right now in the present can cause issues in the future. But the thing is that for these kind of problems, the whole input is known in advance. So if you know the whole input in advance, it's very easy to be greedy, I suppose. It's hard to be greedy if you don't know the future. But for these algorithms, the whole input is already known at one time. So being greedy is actually not a bad idea. So picks the next best move right now, and that's it. So for the most part, at least for in our class, we're going to be using a priority queue to enable a greedy algorithm. So yes, a priority queue is an enabler, and it's an enabler for this greedy approach, not enabling any other type of bad behavior. So the idea is that because a priority queue always maintains the next smallest element, or we can have it as a max heap or min heap, but the idea is that we'll use min heap for right now, or binomial heap or a binary heap, that's a min heap type. It's going to always very quickly pick the next smallest move. And typically for a greedy algorithm, we want to pick the next best move. Our next move is going to minimize our cost. So a priority queue is a very nice structure. It's going to always pick the next best move or next smallest sort of item. So we're going to use a greedy algorithm to do some graph theory problems. So I'll first go over just a problem that's not a graph theory problem, but it is a classic sort of greedy algorithm. So we'll go over Huffman's algorithm. So I guess Huffman was a graduate student in some university, and this was his master's thesis was this algorithm. So basically, this is actually for I think it's for prefix code algorithm. I think that's what it's called. So it's supposed to be so it's supposed to find the minimal prefix code. So we'll go over what that means in a second. Prefix code. I'll write this a little nicer actually. It's actually can be used as a compression algorithm. So the whole idea is let's think of letters, ASCII characters for right now. Let's think of ASCII symbols. So ASCII representation, essentially, using binary numbers. Okay. So for this, the idea is that we have 8 bits we use to represent each binary number, basically. So the idea is, okay, fine, we have a file, let's say we have some notepad file or some file of data with a bunch of characters one after the other. And each character takes up 8 bits. And we can't really do any better because, well, for example, we could have a character with the following ASCII sort of value. I'm just making up stuff right now. So we'll have 1, 2, 6, 7, and we can have, oh, wait, let's think here for a second. Okay, so yeah, so basically, actually, I'm not going to do this. That's a bad example. So the idea is that we have to count every 8 bits to really know the character. We can't do fewer because, well, we don't really know where next character, where it cuts off, next one begins. We have to count 8 characters basically. So the idea is, instead of using, for example, a long 8-bit sort of to store an A, I want to use smaller, less number of characters, less number of binary numbers to store a character. So something like this would be more preferred. What if I have, let's say, like 1, 0, 1, and B is like 0, or something like that. So I could actually have the following string. I could say maybe 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0. Looks like LOL actually, but it's 1, 0, 1, 0, 0. So if we're given this string of digits, we can really tell right away. We can look at this and say, well, that's going to be, so we have a B, B, A, A, B, A, and then B, B. So we can decipher this because we know that B will be 0, A will be 1, 0, 1. So using only these characters, we can very easily tell. And we don't have to use 8 bits to store each of these, which is really nice. But we have to make sure that A and B is in prefix sort of code. So right now, 1, 0, 1, and 0 are not really substrings of each other. Because what if you had the following? What if, let's say, C was the follow? What if we had this? C was actually 1, 0. This would cause some ambiguities, or let's see. This could cause ambiguities. Because what could happen right now is, for example, like right over here, when we have, actually, no, it's not. Hold on, it's not a good example. Let's see. Wait, how about that? There we go. That's going to cause problems. So over here, one is a substring. So if we have, let's say, 1, 0, 1, well, is that going to be just A, or is that just going to be C, B, and then C? It's kind of hard to tell. So you have to, so we're trying to take these, take these letters, and instead of using 8 bits, you want to compress it so every letter will only use a few characters only. But we want to make sure that we know exactly, we can kind of very easily can tell after looking at ones and zeros that what character is it. So you have to make sure that we construct a sort of a sequence, a binary sequence for each letter, such that if we push them all together, it's easily, there's no ambiguities. Like over here, if C was 1, A is B, and then, or B is going to be 0, C is 1, A is 1, 0, 1, we have a problem. We can't really tell if 1, 0, 1 is going to be letter A, or if it's just C, B, and C. So we have to make sure that we can actually construct a normal prefix sort of code. We want to have a minimal prefix code, of course, because we don't want to, you want to use less than 8 bits to store each letter so we can compress the file. The whole point is we can compress this data and be able to still retrieve the letters without needing to have 8 bits for every single letter. So let's go ahead and go over this this algorithm for Huffman's algorithm. Let's go over this and construct this and try to make sense of it. So the way this algorithm actually is going to work is as follows. So we're going to first have, so the first thing we're going to have is we're going to be given a set of characters with their frequencies. So I guess how often this letter appears in certain context, I guess, is really how you want to think about them. So you have a frequency number assigned to each letter, just like that. So given this, we're going to go ahead and try to construct the minimal prefix code for each letter. So we're going to now use this function. It's going to be called Huffman. We're going to pass in C. So C is going to be all the characters, essentially. So I'll put this here in green. It's going to be just the initial given characters with their frequencies. That's going to be what C is that we're passing into this function. Okay. And then we're going to have our priority queue. So we're going to use a priority queue, obviously, because, it's a greedy algorithm. So I'm going to go ahead and just call it PQ for priority queue equals C. So what it's going to do is we're going to take this array of characters frequencies and we're going to do a build heap on this. Remember, I went over build heap. We first started binary heaps, so it's going to do a build heap to just construct a min heap. Construct a min heap of C. So that C array we're going to pass in, and we're going to basically just construct a min heap using that build heap process, because why do it any other way? Because you given the whole array, just remember that build heap, which I went over a few weeks ago, but is what it was. We double down from the leaves upwards, so we have that. So now we have our main algorithm. So we're going to have our main loop here. It's going to have for I equals, I guess, 1 to n minus 1. So this loop will run n minus 1 number of times. We're going to allocate a sort of a binary tree node. So I guess a bin tree node Z or Z. And then what's going to happen is we're going to say, we're going to go ahead and we have these two variables, X and Y as well. So we're going to say Z dot left equals X equals extract min. Priority queue. So we're going to have a variable X. We're just going to we're going to store the, we're going to basically store extract min. So this priority queue is going to be a priority queue of trees. And we'll do the example on this in a second. And we're going to store that root of that tree into X and store it into Z.left as well. Then we're going to get the next smallest element. Just extract min once again. That. And then what's going to happen is Z's frequency, call it Z frequency, will equal X dot frequency plus Y dot frequency. Seems like the book could have just made it Z dot left dot frequency instead, but sure, let's do it like this in the book, so just in case. And then we're going to insert into our priority queue, we're going to insert Z. And at the end, we're going to go ahead and return extract in EQ. I'll go ahead and I'll just sort of put the lines over here. So we have this will be our entire, this will be the entire function body. And then this is going to be the for loop body. So we can analyze the pseudocode for this. So yeah, pretty simple actual, I guess, code for this. So all we're doing is we're going to always take two subtrees of the smallest combined frequency weight, add them together, and put them back into our queue. And keep doing this at the very end. Our priority queue will have only one tree, which will be our final Huffman prefix tree, that decision tree. So of course, I mean, I'll do an example of this because probably the pseudocode itself makes probably no sense at all. But let's go ahead and just I have an example written out over here. Let's go ahead and do an example of this algorithm. So, example. So we're going to have the following. We're going to have A, frequency 45. This is actually from the book. B has 13. C has 12. D has 16. E has 9. F has 5. Okay. This is going to be our C array that's passed into this function initially. And we're going to first insert into our priority queue. So I'm not going to actually show the exact priority queue, the order, but I'm just going to go ahead and just set this up. So here's my priority queue. And we're going to have the following elements in there. So I'm just going to put them in just like this. It's not the actual queue order, but I don't want to spend too much time, showing the entire queue, but just, or showing the order, but just put the queue over here for right now. So these are going to be all sort of subtrees. They're all going to be subtrees right now. Okay, so our first step is maybe look at our, so I guess you can look at I guess we wrote this code down. If not, I'll just, paraphrase it. We first have to do an extract min 2 times. So in this, we have 2 mins. If we do a first extract min, we're going to first extract 5, F5. Then we're going to extract E9. first extract these two. So we're going to first extract min over here. So our first extract min, then our second extract min. That's how the code does this. So we're going to have to combine them together. So we're going to have our Z tree, will be right over here. I'll just maybe just put it as a circle. But Z's weight will be 5 plus 9 or 14. And these two are going to be combined into this one tree. And we're going to go ahead and put it back into our cube. So let me go ahead and actually fix these. So we're going to have first smallest, next smallest. So let's go ahead and now push this tree onto our cube. So I guess maybe I'll use Z, put Z14. Okay, so let's go ahead and sort of redraw our queue, rewrite our queue. So PQ, I'm going to have A45. We're going to have B13. We're going to have C12, D16, and then we're also going to have Z14 with F5 and E9. That's going to be content of our priority queue. Because what we did was we first popped the two smallest elements off. So obviously the root would have F5, and then the root would have E9 after. So we pop the priority queue twice to get to the smallest element and the second to smallest element, and we just combine them together to create this tree. We go ahead and we push this back into our tree, so we end up having this in our priority queue. So these individual nodes are just going to be or these individual numbers will be just leaf nodes, basically. We sort of we have all of these trees in our structure. So again, let's go ahead and pop the queue twice. So our first smallest element will be C12. So I'm going to put C12 over here. And next smallest one is going to be B13. So you can see how we're being greedy. We always pick the two smallest ones, the two best every single time. We're being greedy right now. So what happens now is we're going to go ahead and combine these to make a new sort of subtree. So it's going to be Z25, like that. And then we're going to basically push this into our queue. So let's go ahead and draw the queue below. You have A45 still, D16, then we have Z25, which I will draw this over here, which will have these two children, C12, D13, and then we also have the Z14 with F5 and E9. That's the contents that are on my priority queue. Okay, let's pop the next two smallest elements from our queue. So the first smallest one, I'm going to try to be consistent, so I use red first. The first one's going to be this, Z14. We're going to have Z14, which contains F5, E9. Our next smallest one is going to be D16. So we create another Z we create here. So Z30, we'll combine these two together. Then you push this entire tree onto the queue. So we see every single time you pop two things and push one. So we're going to run this n-1 times. So it'll take n-1 steps. It will take until we have our final answer. We're only going to have one full tree at the very end on this priority queue. We have to sort of do all this work. We're not quite there just yet. But we can see the order, what's happening here. And the priority queue is helping us be greedy. We always pick the next best. Always pick the top two, sort of the two smallest tree weights, basically. So priority queue helps us with this greedy approach. So now we're going to have, I'll put Z30, put this into the queue, which contains Z14, F5, E9, D16 will be in our priority queue. Then we have Z25, which contains C12 and B13. System C12, B13. So these are three elements that are on my priority queue. So next, again, we have to pop our next two smallest elements. Just, we're just basically for most of these greedy algorithms, it's going to be just constantly using the queue to constantly help us pick our next two smallest every single time. So we pop our queue twice. So this will be the first element to get popped off. We have Z25, C12, B13. The next smallest element on our heap will be that one right there. So we're going to have Z30, move over to the right a little bit more, Z30. We have a Z14 over here, D16, F5, E9. I just realized that was not, BWF days. I think F5 was a move by Brock Lesnar. That was his finishing move, I think. If you ever watched WWF when you were a kid, I'm old enough to remember that. That's what F5 reminded me about. It seemed kind of odd. Let's move this down a little bit. Space here. Then we're going to combine these two. So we're going to make a new node Z, which will be 55, I believe. And we combine these two together. As a result, I'll put it down a little further down so it's not really too close to the queue. Down further even. It's a little bit out of the way, so it's not going to confuse us. We're taking notes. So now, our priority queue, we're going to go ahead and push this back on. So I'm going to actually, so I'll rewrite this, sure. So PQ will have A45, and then it will have this entire tree. So Z55, Z25. Actually, I'm going to go ahead and just sort of copy this entire thing instead of write the whole thing out. Just copy and paste. This is, yeah, I don't want to. Here. Sort of really quickly. There we go. So it's going to be the contents of my priority queue now. So now at the very end, we have only two sort of trees left. So we're going to pop these both off. We're going to first pop A45 and then Z55. It's going to basically, I'm going to just, again, just copy this instead of redraw the entire thing to make it a little faster. I'm going to go ahead and put this over here. I think it's supposed to go to the right because this is a larger tree, I think. Then we have A45 here. Again, another Z sort of tree again. This will be Z 100. And there's our final tree. Let's go ahead and just sort of Yeah, and this would go ahead and get pushed onto the queue. Actually, I should have done this. Should have color coded this. Okay, my mistake. It's supposed to be red. It's all supposed to be blue. It's consistent with the rest of the example. So we had these two trees. We popped these two trees off, combined them, and then we put it back into our queue at the very end. Then we're done. Queue equals, then we go ahead and sort of push this final tree at the very end. To the left, that. OneNote can be nice, but also can be a pain sometimes too. And then at the end, we just n minus one number of times, and it's going to return this tree, essentially. That's going to be our result. So basically, we go ahead and actually sort of, look at this copy this again. So at the very end, this is going to be a final result or one tree by itself. So I'll put this here also to help it with note taking. The final result is going to be this tree, which I'll paste it again over here. That. So basically, how we can look at this is we can sort of create a decision tree out of this and just use the left branches will always be zeros like this. And the right branches are going to be ones. So if you follow these paths, this is going to give you the it's going to give us basically the prefix code for every single letter. Now, I guess I'm kind of low on time here. I'll just do one example about probably in the video that I'm going to post, or pre-record video for Tuesday. I'll sort of continue with this and then continue further. But in this case, A has the prefix code of just 0. And then I guess B, well, B is right there, so it's going to be 1, 0, 1. C is going to be 1, 0, 0 if we follow those branches. 0, 0. D is going to be 1, 1, 1. E is going to be 1, 1, 0, 1. And then A, B, C, D, E, and F is going to be 1, 1, 0, 0. And then we can actually use these digits, these binary numbers, to represent each letter. And they're not going to have any overlap with each other. So none of these has any, they're not substrings of each other, basically. So I guess I'll do examples of this in that video. But this is a way where we can take these 8 bits that's mostly used to store a number. We can compress it using 4 bits or less. So that way we can compress a data file with characters, and we can easily expand them because we know a 0 by itself will be A. If you see a 1, 0, 1, that's a B. So we can expand them very easily. So I'll sort of go over that later on. But I guess that's going to be it for today. So remember, next week Tuesday, there's no live class. I'll have a pre-recorded video. Next Thursday will be no class at all, Veterans Day. So there's no live class at all next week. I'll have a homework assignment still posted up next week on sort of depth first search type of content. Other than that, take care, you guys. Thanks for watching. Stay safe. Have an awesome weekend. And I'll see you guys later on. Take care.